Hi, I'm glad to see you again here in the WebAudio conference, and thanks our work on the FAUST IDE and the WebAudio plugins, I've been working on the project called JSPatcher, which is a visual programming language VPL on the web for audio processing and some more general usages. I know that there are already many of them in the domain to facilitate web audio connections, to process or generate sound or image, and so on. So in the beginning of my project, I was planning to bring this VPL to another level, being different from most of the existing web audio VPLs. So let me start from introducing why and how it could be different. I think we might not need to take time to discuss the importance of VPLs in audio-related work. WebAudio itself is graph-based, so having a graph editor to work with WebAudio is quite natural. I can list some useful tools like WebAudio Designer, G-Sync Lab, WebAudio Graph Editor, and so on. There are also some higher-level VPLs on the web like Eternal, Wasabi Pedalboard, or Cables.gl. They can be used to create multimedia contents. So these platforms are interesting for people from different backgrounds to quickly get into web audio and do some experiments. However, if we ask real composers who produce interactive music, they might be more familiar with Max or PureData. At least I was using them quite a lot while composing music, because we can not only connect DSPs between each other, but trigger in real time non-audio events or calculations, which is essential to some interactive art project. In fact, the reason I make another VPL is that I think the current ones were not flexible enough for artistic projects due to the lack of non-audio calculations. Fortunately, we are in the JavaScript environment, so there should be an easy way to have a graph that treats non-audio values or events. So the first version of JSPatcher is basically a web audio graph editor with event triggering from users and non-audio calculations. The interface and the rules of patching are similar to Max or PureData, so that users can quickly understand the mechanism. It means there is different priority between cables. The text in the boxes will be passed into three parts: class, arguments, and properties. And there is a special event called ban, which is an empty event to tell any box object to start its function. But only these operators are obviously not enough, because we will need much more than just basic calculations. Actually, the whole ECMAScript standard and the Web API are all available here, and we should be able to use all of them. So in the second version of the JSPatcher, we imported nearly every JavaScript built-ins and Web APIs from the global scope into the environment. Then they can be connected as boxes in the patcher. We don't have much time to explain how this works, but here's an example of lambda function that is used by ArrayReduce. So in the reduce, the lambda function takes two arguments, one for the accumulated value and another for the current value iterated. The lambda function is generated by this lambda box declared as two arguments, which can be get from last two outlets. Here we already created this float32 array with 256 elements and filled it by plenty of 2. If we need to calculate the sum of this array, all we need to do is to add these two arguments together and return it to the lambda box second inlet. So this mechanism means that external JavaScript modules can also be loaded dynamically in the patcher. So here is an example using Three.js to create WebGL graphics. Now we set up a camera, a light, a material, and a cube mesh. Finally, add them to our scene. We are using request animation frame with a lambda function that will be called each frame to rotate the cube. Okay, so now we are having a graph-based VPL with two parts working together, a web audio graph connected with audio nodes and a dataflow graph that triggers and treats events from data. Good, but we still don't have a way to customize DSPs with AudioWorklet. So I introduced here a third part in JSPatcher, which allows to compile a subgraph to a DSP module. Knowing that in Macs there's a system called Gen that allows to design a DSP without coding. The user just connects functions with cables, and the tool will automatically generate the corresponding code and compile the DSP. And here we are doing the same and using FAUST as an intermediate language between the graph and the AudioWorklet DSP. The usage is quite similar too. Here, each box represents a function that takes some arguments or inlets. Note that a predefined argument will replace an inlet into a constant value. When the program analyzes the graph, it will iterate all the outputs and search the connections above. So without any connection, its inlet will be the default value 0. Then multiple connections into the same inlet will be merged and added together. If you need to introduce a loop into the graph, it should be delayed by at least one sample by tilde operator. The system supports two types of subprocess. You can use a code box to write false code directly, or put a graph in the subpatcher. These subprocesses are especially useful when you want to reuse it in different situations. As we are now based on the FAUST language, we can also have a lambda function that will be iterated multiple times in the FAUST patcher. This doesn't exist in Gen, but I found quite useful. And we can also declare some UI components that's like sliders, buttons, groups, and so on. The corresponding UI can also be generated in the web page. Once the graph is connected, the corresponding false code is generated and compiled to an AudioWorklet node immediately. We can now use the node in the normal patcher with other web audio nodes. We're also working on some embedded tools or objects for musicians like audio file editor or score visualizations. We invite you to try out and comment on our GitHub project. Thank you for your listening.